Learning physics is not rocket science. It's easier than saying super califragilisticexpialiticus. Let's begin with this dude. Some people call him Isaac Newton. So one day, Newton is sitting under a tree, but when an apple hits his head, instead of eating it, he decided to figure out why it fell, and therefore, he decided to invent physics. Thanks, Newton. Well, first we need to start with forces. Imagine you're pushing a shopping cart. Easy, right? But then, out of nowhere, friction shows up and says, "Not so fast, buddy." Friction is that force that resists motion, like when you're trying to slide across the floor in your socks, and you just stop. But don't worry, we've got Newton's laws to help us out. Newton's first law says that an object in motion stays in motion unless acted upon by an external force. So, if you push that shopping cart and nothing gets in the way, it'll keep going. But thanks to friction, it eventually stops. Thanks a lot, friction. Now, let's look at Newton's second law. It's like the physics version of the more you eat, the more you grow. The more force you apply to an object, the more it accelerates. Simple, right? But then there's mass. Mass is like that friend who never wants to go anywhere. The more mass an object has, the harder it is to move. So, if you're trying to push a boulder, good luck. You'll need a lot of force to get that thing moving. Newton's second law can be added together with the equation called force equals mass times acceleration, where F is force, m is mass, and a is acceleration. So, if you want to move that boulder, you need a big F. Alright, finally, we have Newton's third law. This one is my favorite because it's all about action and reaction. But how? For every action, there's an equal and opposite reaction. It's like the universe's way of saying, what goes around comes around. Imagine you're on a skateboard and you push against a wall. What happens? You roll backward. That's Newton's third law in action. The wall pushes back with an equal force, sending you in the opposite direction. But what about when things get a bit more complicated? Like when you're trying to figure out why your skateboard stops rolling. That's where friction comes in. Friction is the universe's way of saying, slow down, buddy. Friction is a force that opposes motion. It's why you can't slide forever on a skateboard. The rougher the surface, the more friction there is. So, if you're skating on sandpaper, good luck with that. Alright, now you know what friction is, let's look at a little bit of energy. No, not the kind you need to get out of bed in the morning. We're talking about kinetic and potential energy. Kinetic energy is the energy of motion. If you're running, you have kinetic energy. Potential energy is stored energy, like when you're at the top of a slide, just waiting to zoom down. But what happens when you go down the slide? That's where the law of conservation of energy comes in. It says that energy can't be created or destroyed, only transformed. So, your potential energy at the top turns into kinetic energy as you slide down. Think of it like this. If you eat a candy bar, potential energy, you can run around like a maniac, kinetic energy. But if you eat too many candy bars, therefore you'll just sit there with all that potential energy and no motivation to move. Balance is key, but there's still more. Momentum, let's break this down. Momentum is mass in motion. The more mass and speed you have, the more momentum. It's why a speeding formula, F1, has more momentum than a speeding bicycle. But what happens when things collide? That's where the conservation of momentum comes in. It says that the total momentum before and after a collision is the same. So, if two bumper cars crash, their combined momentum stays the same, even if they bounce off in different directions. Imagine you're playing pool. When the cue ball hits another ball, the momentum transfers. The cue ball slows down, and the other ball speeds up. It's like a perfectly choreographed dance, but with more clattering and less grace. With all that talk about bumper cars, I think it's time we talk about thermodynamics. Imagine you're at a party. Energy is like that one friend who can't sit still and has to talk to everyone. It moves from one place to another, making things happen. But wait, there's more. Just when you thought you had it all figured out, here comes the first law of thermodynamics. Now, if you have listened to this video carefully, then you must have come to know that I had already mentioned this law in this video, which is the law of energy conservation. Sounds fancy, right? Now, let's throw a wrench in the works with the second law of thermodynamics. This one says that energy likes to spread out and get all disorganized like your room after a weekend. It's called entropy. And no, it's not a new dance move, although it would be a pretty cool name for one. So, how do we deal with this entropy business? Well, we can't stop it, but we can understand it. Think of it like trying to keep your room clean. You can tidy up, but it will always get messy again. The universe is kind of like that, always moving towards more disorder. Feeling like a thermodynamics pro yet? Hold on, because we're not done. Let's look at the third law of thermodynamics. This one says that as things get colder, they get more ordered. So, if you ever feel like your life is chaotic, just remember, at absolute zero, everything is perfectly in order. Too bad we can't live in a freezer. But wait, there's a twist. The zeroth law of thermodynamics. Yes, they named it zeroth because they thought of it last. This law is all about thermal equilibrium. If two objects are each in thermal equilibrium with a third object, they're in thermal equilibrium with each other. It's like saying, if you and your friend both like the same pizza, you both have good taste. So, what does this mean for us? It means that temperature is a thing, and it's important. It's how we measure how much energy something has. Alright, let's get into electricity. You know, that thing that powers your video games and keeps your ice cream from melting in the fridge. Electricity is all about the movement of tiny particles called electrons. But wait, there's more. Electricity and magnetism are like the peanut butter and jelly of physics. They go together perfectly. So, let's see how they team up. Now, you might be thinking, okay, electricity is cool, but what about magnets? Are they just for sticking notes on the fridge? Well, magnets are way cooler than that. They have this invisible force field around them called a magnetic field. It's like a superpower, but for metal objects. Not for this object. And here's where it gets interesting. When electricity flows through a wire, it creates a magnetic field. And if you coil that wire around something metal, like a nail, you get an electromagnet. Boom! You've just made a magnet that you can turn on and off with electricity. Try that with your fridge magnet. So, we've got electricity and magnetism working together. But what happens when we mix them up even more? Therefore, we have electromagnetic waves. These are waves of energy that travel through space. They're the reason you can listen to music on the radio, watch TV, and even use your microwave. Without electromagnetic waves, you'd be stuck reading books for entertainment. Yikes! Electromagnetic waves are created when electric and magnetic fields dance together. These waves come in different flavors like radio waves, microwaves, and even light waves. So, next time you zap a burrito in the microwave, thank electromagnetism. I think you know this guy. This guy tells us that time and space are not as rigid as we thought, they're more like a stretchy rubber band. When you're moving fast, time slows down and lengths contract. But wait, there's more. What if I told you that distances can also change? Yep, it's not just your eyes playing tricks on you. This is called length contraction. Let's break it down with an example. Imagine you're holding a ruler while zooming past your friend at nearly the speed of light. To you, the ruler looks normal, but to your friend, it looks shorter. No, your friend doesn't need glasses. It's just relativity doing its thing. But wait, there's still more. Just when you thought you had a handle on special relativity, Einstein throws general relativity at you. This is where things get interesting. So you probably know that apple falls into Newton's head. But why? You might say gravity, but what if I told you that gravity is a warping of space and time? Mind-blowing, right? Imagine a trampoline. If you put a heavy ball in the middle, it creates a dip. Now, if you roll a smaller ball near the edge, it will spiral toward the big ball. That's exactly how gravity works. Massive objects like planets and stars warp the space around them, and that's why things fall towards them. Now you know that I mentioned this famous equation. This equation might look like a random string of letters and numbers, but it's super important. It tells us that energy and mass are interchangeable. Think of it this way. If you could convert a tiny bit of mass into energy, you'd get a huge amount of energy. That's why nuclear reactions are so powerful. They convert a small amount of mass into a massive amount of energy. By the way, talking about nuclear, I think it's the best time we talk about nuclear physics. So this is an atom which is made up of electrons, protons, and neutrons in the center. There is a nucleus, you know, that tiny thing in the center that holds protons and neutrons together. The nucleus is like the VIP section of an atom. Only protons and neutrons are allowed in. Electrons? They have to stay outside in the electron cloud. Poor electrons are always left out. But wait, what keeps these protons and neutrons together? Shouldn't they just fly apart? After all, protons are positively charged and should repel each other, right? Enter the strong nuclear force. It's like the bouncer at the IP section, making sure everyone stays in place. This force is incredibly strong, but only works at very short distances. It's what keeps the nucleus from falling apart. Think of it as the ultimate superglue. Now that we know what holds the nucleus together, let's talk about what happens when things go wrong. Sometimes, the nucleus can become unstable and decay. This is called radioactive decay. It's like when you leave milk out too long and it goes bad. Gross, but fascinating. But how do we measure this decay? How do we know how fast it's happening? We use something called the half-life. It's the time it takes for half of the radioactive atoms to decay. Imagine you have a bag of popcorn. After one half-life, half of the popcorn is gone. After another half-life, half of what's left is gone, and so on. Eventually, you're left with just a few kernels. Now, let's get into the fun part. Nuclear reactions. There are two main types, fission and fusion. Fission is like breaking a chocolate bar in half. Fusion is like like melting two chocolate bars together to make one big bar. Both release a lot of energy, but in different ways. But how do we calculate the energy released in these reactions? Therefore, we use Einstein's famous equation. This equation tells us that energy is equal to mass times the speed of light squared. It's like saying the energy in a chocolate bar is equal to its mass times the speed of light squared. That's a lot of energy. Hey, can we go back to neutrons and protons? What are they made of? Neutrons and protons are made of quarks. Well, quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Yeah, I know it sounds like a weird ice cream menu, but these flavors are just different types of quarks, and they combine in different ways to make protons and neutrons. For example, a proton is made up of 2 up quarks and 1 down quark. Simple, right? But wait, there's a problem. How do these quarks stick together? I mean, they can't just be floating around like confetti at a party. This is where gluons come in. Gluons are like the glue that holds the quarks together. Without gluons, the whole party would fall apart, and nobody wants that. So, gluons keep the quarks together, and everything is hunky-dory. But there's more to the story. Quarks and gluons are part of a bigger picture called the Standard Model. Think of the Standard Model as the ultimate guest list for the particle party. It includes all the particles we know about and how they interact with each other. Now, we have 4 fundamental forces: gravity, electromagnetism, the strong force, and the weak force. But I already explained gravity and electromagnetism. Therefore, we have a strong force. It's the bouncer keeping the quarks in check. And the weak force? Well, it's like the party planner, making sure everything runs smoothly. But here's the kicker. Even with all these forces, particles can be unpredictable. Sometimes they decay into other particles. This process is called particle decay. To understand particle decay, we use equations. And the equation is this. Yeah. Again, this equation also tells us that energy and mass are interchangeable. So, when a particle decays, its mass is converted into energy. Finally, we have the Higgs boson. This particle is like a VIP guest. It gives other particles their mass, which is kind of a big deal. Without the Higgs boson, particles would be massless, and the buttverse would be a very different place. Now, the end part of this video, we have quantum mechanics, which I will not explain in this video because I already explained it, but in this video. So click on this video to learn about quantum mechanics.